Okay, we're going to look at one more example of addition reactions to alkenes. In this case, we're going to talk about dihydroxylation. So dihydroxylation is the addition of two OH groups to our double bond. And we can do dihydroxylation in an anti-form or in a syn form. And so if we look at the anti-form, right, 1 OH on the wedge, 1 OH on the dash. So I'm going to go through the mechanisms for the anti and the syn dihydroxylation, but I'm not going to make you responsible for the mechanism. So if you're in my class, if you want, you can take kind of light notes until we get to a slide where I talk about the take-home message and do some examples. Or if you want, you could probably just skip to the part of the video where I give sort of a take-home message and then do some examples. Okay, in anti-dihydroxylation, we're going to use a peroxy acid as our reagent. And the peroxy acid, right, we have two oxygens bonded to each other, and so this is the peroxide group, right, and then we have the H here that makes it an acid, and then we also have the double bond O here. And so this is sort of a similar to a carboxylic acid, but instead of just being an OH, we have this peroxide. And so when we use this peroxy acid as our reagent, we form an epoxide as an intermediate. Okay, after we form this epoxide, it's reacted with water and an acid catalyst to form the anti-diol. So we haven't named alcohols yet, but alcohols names end in OL, so a diol is two OHs, or two alcohols in the same compound. And so the mechanism, right, first we have the acid that protonates our epoxide. We then have a nucleophile come in, and so the reason we get anti-addition with this peroxy acid is because after we form the epoxide, right, the nucleophile has to come in from the backside. After the nucleophile attacks, we then have a final proton transfer to regenerate our acid, making it a catalyst, and then we get the anti-addition of the two OH groups. Right, so this protonated epoxide as an intermediate probably looks similar because we saw similar intermediates in the case of hydrogenation and in the case of oxymercuration, demercuration. And so the ring strain and the positive formal charge make these good electrophiles, so they're vulnerable to nucleophilic attack. And then they also all yield anti-products because the nucleophile has to come in from the backside because this bridge structure blocks it from coming in on the top. Okay, so the reagents that lead to syn-dihydroxylation are these osmium compounds. And so because both oxygens that we're adding are coming from the same compound, that leads to the syn addition, where both OHs are attached to the same side. So we first produce this cyclic osmate ester, and then we'll react it with sodium sulfite or sodium hydrogen sulfite to pop off the osmium and leave our two OH groups that are on the same side. And so it yields to syn addition. So using large amounts of this osmium compound is problematic. For one, it's very expensive. For another one, it's highly toxic. And so we want to minimize the amounts of this that we use. And so very often we use a compound NMO, structure is given here, or an alkyl peroxide as a co-oxidant. And in that case, we can only have to use catalytic amounts of the osmium compound to produce the syn addition. Another reagent that will give syn addition is permanganate, but permanganate is highly reactive, and so it will often react with many of the other functional groups in the molecule, so that can sometimes limit its utility, but in the cases where we can use it, use of the permanganate ion also gives syn addition of the two OH groups. Okay, so this is really the take-home message. If you see an alkene being reacted with a peroxy acid and then hit with an acid catalyst, that's going to yield the anti-addition of the two OH groups. If you see this osmium compound or potassium permanganate used as a reagent, that's going to give dihydroxylation, but it's going to give the syn addition. Now, just like the other reactions that we've looked at in this chapter, we do have to be aware of the stereochemistry, right? And so whether we have whether we have anti or syn addition, we want to be sure and check and see whether or not we have a chiral molecule or not. In this case, we do, and so we'll also get the enantiomer where this OH is on the dash and this one is on the wedge, right? In this particular example, we formed a meso compound because we have a plane of symmetry in the middle. So in this case, we just get the one product. It's not chiral because it's meso, and so it does not have an enantiomer. Okay, so let's look at a couple examples. So we want to predict the products of this reaction, and so I see I'm reacting it with a peroxy acid and then hitting it with an acid, and so this tells me that I'm going to be doing dihydroxylation, but I'm going to add the two OH groups in an anti-fashion. So my product, and again, when I choose to add these groups, right, the wedges and dashes, I'll do my OHs, and then I'll use the lower priority group. So I'll mess with the methyl being on the wedge and the dash, and the hydrogen being on the wedge and the dash on this one. So we have anti-addition. So if I put my first OH coming from the top, that pushes the methyl down. And then because we're using a peroxy acid, I know that this is going to be the anti-addition. So if the first OH comes in on a wedge, then the second OH has to go in on the dash. All right, now this compound has two chiral centers. It's not meso, so we'll get this compound and its enantiomer. So we'll also get the product where this OH is on the wedge. In this case, the methyl's on the wedge. Oh. Don't know what happened there. And that OH goes on the dash. Okay, so here's another example. Again, I'll be doing the anti-addition, although in this case, right, we're going to have a chiral carbon produced in the product here, but this carbon is going to have two hydrogens on it, and so it's not going to be chiral. And so whether this is syn or anti doesn't really matter. But our products, I can get one OH here because this carbon, even when I put the OH on it, it's still going to have two hydrogens. It's not going to be chiral, so right, I don't need to worry about the wedges and the dashes. But this carbon is chiral, and so I will get the enantiomer, and so I'll also have that OH on the dash. Okay, one more example. In this case, right, I see this osmium compound, so that tells me that I'm going to be doing dihydroxylation, but the OHs are going to be added in a syn fashion, and so my product both OHs come on the wedge. Now I do have two chiral centers, but I also have this plane of symmetry, and so this compound is meso, so it does not have any enantiomers, and I just get the one product.